Good morning. Okay, let's just wait for everyone to get here, then we can start. Okay, so last week I assigned homework 3, I believe. So that's due on Tuesday.
No.
Homework 4, sorry, homework 4. Most of homework 4 I assigned last class. Okay, good. Yep, so homework 4 except 4.4 is assigned for Tuesday so far. Okay, let's get started. Okay, so this is lesson 12. Okay, so last class we finished 4.3. So last class we were talking about discrete random variables. So let me get the, okay. So last class we talked about discrete random variables, right? What it means for a set to be discrete. We already talked about that. Okay, and so that was the main point of discussion. This class, we're going to talk about probability histograms. And bar charts. We're also going to talk about the discrete uniform distribution. Okay. The Bernoulli distribution. And binomial distribution. And then if there's time, we're going to talk about sampling with and without replacement. Okay. And then if there's even more time, we can talk about more things. Okay, so let's start with probability histograms, and nobody else is here yet. Okay, so let's start with 4.4 probability histograms and bar charts. Okay. So I'm going to do on the whiteboard is draw an example of both a probability histogram and a bar chart. So let's go to the whiteboard. Okay, so to the whiteboard, so you have the y-axis, you have the x-axis. So let's say you take the experiment of rolling 2 dice, right? Two fair 6-sided die, okay? And then you add up the sum of the 2 dice. Okay, so you add up the sum of 2 dice, you roll 2 dice, and you take the sum. Possibilities of the sum are 2 through 12. Okay, so possibilities of the sum are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? Because you can roll a 1 and a 1 and get a 2. You go roll a 1 and a 2, and get a 3, 2 and 2, and you get a 4, and so forth, up to and including 6 and a 6, and get 12. So the sums range from 2 to 12. You can't get larger than 12, and you can't have a sum of 1 because each dice is at least 1. Okay. Now, another class, we found the probabilities of each of these things. Right. So what I'm going to do here, though, is say we already have those probabilities, and we're just going to use the bar chart to express them. Okay. Uh, so the probabilities we had were 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 over 36, and 6 over 36. Okay. And so uh, this is going to be an example of a bar chart. Okay. It's easy to get a bar chart and a histogram confused between one and the other. I don't know if the screen's moving around for you. I'm trying to fix. Okay, you should be able to see the whiteboard. So the sum of 2 dice, it has a 1 over 36 chance of happening. And so to express that, you just draw a bar like this. Okay. So this is an example of a bar chart. Oh no, sorry. This is, like I said, this is probably a probability histogram. Okay, so this is an example of a probability histogram. Okay, so here the probability of getting a sum of 2 dice is 1 over 36. Probability of getting a sum of 3 is 2 over 36. The probability of getting a sum of 4 is 3 over 36. Probability of getting a sum of 5 is 4 over 36. The probability of summing a 5 is sum of 6 is 5 over 36. Probability of the sum of 7 is 6 over 36. The sum of 8 is 5 over 36. Probability of the sum of 9 is 4 over 36. Probability of the sum of 10 is 3 over 36. Probability of the sum of 11 is 2 over 36. And the probability of the sum of 12 is 1 over 36. Okay, so usually you draw the bar halfway between each number, right? So doing it on the screen, I have it like this. So this is an example of a probability histogram of this experiment, right? Where the height of the bar, the height of this thing is expressing the probability of each of these simple outcomes. Okay. Right. So any questions about a probability histogram? This is an example of a probability histogram. It looks like they look like bars, so it looks like it might be a bar chart. But here, notice that this rectangle is centered at that number. Okay. So this is an example of a probability histogram. Next, let's do an example of a bar chart. So same situation. You roll 2 dice, and you want to draw a bar chart of the same situation. So you have the sum of 2 dice. Possibilities for the sum are 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay. And so the probabilities that we put here, 1 over 36, 2 over 36, 3 over 36, 4 over 36, 5 over 36, and 6 over 36. Okay. And so these are going to be values of f of x, the probability distribution function. Okay, so this is 1 over 36, This is 2 over 36. 3 over 36. 4 over 36. 5 over 36. And 6 over 36. Okay, and so these are the probabilities of each of these sums. So I guess I'm gonna draw in pink, and I'm gonna draw this as just being wider. So I'm gonna draw the bar vertically above 2. So this height of this is the bar, and this is 1 over 36. Let me label this also. This is a bar chart. Okay, the bar is going directly over the number while the histogram, the rectangle, is kind of centered at it. Okay, so this is an example of a bar chart. Okay, these are probabilities. Okay, so then the height at 3 is 2 over 36. The height over 4 is 3 over 36. The height over 5 is 4 over 36. The height over 6 is 5 over 36. 6 over 36. 5. Okay, this is going to be 4. It's 3. That's 2. Oh, and there's one more. Okay. And this is 12. There we go. It's also so 12, and then above that is the bar 1 over 36. Okay. I just put pink here. That way I could differentiate between the black I drew here and the bar itself. Okay. So the height of the bar will tell you the probability. So for instance, here. So for instance, here, right? Don't draw the dotted lines, but I'm just pointing out, right? So for a sum of 6, the height of the bar is 5 over 36. That tells you that the probability of a sum of 2 dice being 6 is 5 over 36. And I'm going to get rid of the dotted line. Okay, and that's it. And the other heights, corresponding heights, will give you the corresponding sum and probabilities. Okay. Any questions about a bar chart? Okay, they're each easy to draw. It's just sometimes it can be confusing which one is which, right? The bar looks like this, and I guess you can see how this could be a bar, but with the probability histogram, this also kind of looks like a bar. So, but this is how the probability histogram is drawn. That's the bar. Probability histogram, bar chart. Okay, so I'm glad I'm done drawing that, and so let's just pictures illustrate that. So on the whiteboard is illustrated both. Okay, so section 4.5. Just checking everything. Good. Okay, nobody's waiting. So section 4.5 is on several important discrete distributions. Okay, so we're going to look at several important discrete distributions. We're going to look at them one at a time. So the first one we're going to look at is the discrete uniform distribution. Okay, so right now we're living in a discrete sample space. Okay, so that means that reminder, a discrete it's a discrete random variable is a random variable, which I'm not going to go into the definition of random variable. What I want to do is just talk about a discrete for a second. A discrete random variable is a random variable for an experiment with a discrete sample space, right? Just remembering a discrete part with a discrete sample space, right? a discrete sample space is a sample space that is either finite or countably infinite. Okay. Okay, so let's talk about 4 point. So, oh, that, sorry. Okay, so consider the experiment of selecting a number at random from the set consisting of the numbers x1 to xn. Okay, so there's a total of n of them. Sorry, just I don't know why it's capitalizing. There we go. Let capital X be the value of the number selected. If we assume that each of the numbers x1, x2, and so forth, xn has an equal chance of being selected, then f of x sub I, f of any of the x values, is equal to the probability that the random variable capital X is equal to that number selected, right? X is the value of the number selected, so the probability of capital X being one of those x values is equal to 1 over n. And this is for I equaling to 1, 2, and so forth, up to including little n. Okay? So let capital X be the value of the number selected. If we assume that each of the x values, x1 to xn, has an equal chance of being selected, then the probability of choosing one of them is 1 over n. There's n of them. There's little n of them, right? There's x1 to xn, right? So as an example, let's suppose that little n is equal to 3, right? Then your set would consist of the numbers, the values, x1, x2, and x3, whatever they are, they're random, they're variable values, right? So that would be your set. And then capital X is the value of that, right? So f of xi would equal to, which is equal to the probability of capital X equaling one of those x values, is equal to 1/3, right? And that's for I equals 1, 2, or 3. Right? So for I being either 1, 2, or 3, f of x sub I is 1/3. There's 3 values. The probability of getting one of these 3 values is 1/3. Okay, that's all that's saying. Very simple. Okay. Okay. So this probability function is called the discrete uniform probability function / distribution. Okay, uniform because the probability of each possible value of capital X is the same. That's the uniform part of the name. Okay, discrete because the sample space, the possible values of X is finite. It's only little n many possible values of capital X. And so there's only little n simple outcomes in the entire sample space. So discrete, uniform, probabilities are the same, and it's a probability function. Okay, also called the distribution. So let me define, but the definition is that it's definition 4.3. I'm just going to kind of re-say what I just said. The function f of x sub I, which is equal to 1 over n, positive integers n, such that I is the possible values of I are 1, 2, 3, and so forth, up to and including little n, is called the discrete uniform probability function. Okay, so that function is called the discrete uniform probability function. Okay, so that's the definition of a discrete uniform probability function. And so a random variable, capital X, has a uniform, has a discrete uniform distribution and is a discrete uniform random variable if its probability function is the discrete uniform probability function. So what this is explaining or defining is when does a random variable x have a discrete, when is a random variable x a discrete uniform random variable? So if you have a random variable x and its probability function is the discrete uniform probability function, then x is a discrete uniform random variable and it has a discrete uniform distribution. Okay, so you're just looking at the probability function of your random variable. If it's the discrete uniform probability function, then you have a discrete uniform random variable, and the function, the probability function, is the discrete uniform probability function. Okay. Part of the statement is saying if the probability function is a discrete uniform probability function, then you have a discrete uniform probability function, right? So, okay, so it's kind of stating the obvious, but stating the obvious is sometimes important. Okay, so next is 4.5.2, the Bernoulli distribution. Okay, so here's an example that uses it. And so an experiment consisting of only two possible outcomes, either success or failure, is a Bernoulli trial, right? So we talked about that in other classes. If capital X is a random variable that takes on a value of 1 when the Bernoulli trial is a success, and a value of 0 when the trial is a failure, and capital X is a Bernoulli random variable. If P is the probability of success and Q equals 1 minus P is the probability of failure, then f of x is equal to so f of x is equal to P if x equals 1 and Q if X equals 0. Okay. Okay, so the probability of success is P and the probability of failure is Q, but it takes in a value 1 for a success and a value of 0. Capital X takes a value of 0 for failure. Okay, so this probability function is called the Bernoulli probability function / distribution. Okay, so now I'm just going to reiterate what I said. Definition 4.4, the function f of x is equal to p if x equals 1, q if x equals 0, where 0 is less than p less than 1, and p plus q is equal to 1, is called the Bernoulli probability function. Okay, so without even saying the words success and failure, we're expressing the idea of success and failure as kind of two opposite outcomes of the experiment, right? And the value in one of them is a 1, and the value in the other one is a 0. So capital X, our random variable, or discrete random variable, can only take on two values, 0 or 1. Q is the probability of a 0, of X being 0, and P is the probability of X being 1. And so we're not using the word success and failure. We're expressing that idea as just two polar opposite outcomes, right? 0 or 1, two possible outcomes, right? Where P, the probability of a 1, is strictly between 0 and 1, and the P plus Q is 1. So if P was 0 or if P was 1, that would imply that Q would be the opposite 1 or 0, right? So that would really mean that one of these values couldn't happen. And so you'd only have one possible value and it would always happen. That would be a constant function, right? And so you don't want little p to be able to be 0 or 1, okay? So you want strictly between 0 and 1. And that allows the possibility of a second distinct possible value of capital X with a positive probability, right, of happening, of being assigned that value. Okay, so that's why little p has to be strictly between 0 and 1. We want two possible values of capital X. So your question is saying it's only for success and failure. So what I'm saying is that here I'm defining it to be values 1, X being 0 or 1, right? I'm never saying the words success and failure. So the answer to your question is no, it's not always for success and failure outcomes only. In general, it's just two possible outcomes, right? Two possible outcomes. Either one thing happens or the other thing happens, right? But usually, a lot of times, this is used in a situation where you would say one is a success and one is a failure, right? So we'll see examples, right? But usually the most common way you would have two possibilities is just you either succeed or you fail, right? And so the word success and failure are kind of expressing the idea of two possible possibilities, right? So in general, what we're really talking about is only two possibilities, right? Each have a chance of happening, okay? but one way to express that is success and failure. Okay, so I think you get what I'm saying. Okay, so it's not necessarily success and failure, but you can think of it oftentimes as success and failure. Okay, so a random variable, capital X, has a Bernoulli distribution and is referred to as a Bernoulli random variable if its probability function is the Bernoulli probability function. Okay, so this is just like the other statements I've made. What we want to reach, the conclusion we want to reach, is that a random variable X has a Bernoulli distribution and is a Bernoulli random variable. That happens if its probability function is the Bernoulli probability function. Okay, if you have a random variable and its probability function is of this form, then you can conclude you have a Bernoulli random variable and its distribution is a Bernoulli distribution. Okay. Okay, so this is all kind of more terminology. Okay, 4.5.3, their Bernoulli distribution. Okay, so let's study the Bernoulli distribution or Bernoulli probability function, the one we just talked about here, this guy, right? Okay, so the Bernoulli distribution. Okay, so consider n Bernoulli trials. These are trials, when you do an experiment, the trials have two possibilities, right? Which is also expressed as success or failure. So if S sub n, if capital S sub n is equal to the total number of successes in the n Bernoulli trials, what is the probability function of S sub n? Okay, what is the probability of S sub n equaling to x, little x, for x values, little x values to be 0, 1, 2, and so forth, up to including little n? Okay, so I'm going to label this as a question. We want to answer. Okay, so the question is, consider n Bernoulli trials. If S sub n is the total number of successes in the n Bernoulli trials, what is the probability function of S sub n? What is the probability S sub n equals little x for x from 0 to little n? Okay, you have n Bernoulli trials, right? Each Bernoulli trial is characterized as something that has either success or failure, not both. Okay? Well, if there's n of them, and you want to think about how many successes you could have, well, either you have 0 successes, you always fail, right? Or you have 1 success, or 2 successes, and so forth. And if there's a total of little n Bernoulli trials, you could succeed at most little n times. So little x is going to denote the fixed number of times you succeed. And so the possible values little x could take are from 0 to little n. Okay? And capital S sub n, which is the total number of successes, you want to know the probability of S sub n is equaling to some little x, where little x ranges from 0 to little n. Okay? This is expressing the probability that the total number of successes in the n Bernoulli trials is either 0, 1, 2, and so forth up to n. Okay? Okay, so just explaining the notation. So explaining the notation, the probability of S sub n equaling to little x is equal to the probability that in little n Bernoulli trials, you have little x many successes. You have exactly little n successes. Exactly little x many successes. Where little x takes on any value, any integer value between 0 and little n inclusive. Okay? Meaning it could take on values of 0 and little n. Okay, so that's explaining that notation. So let's find this distribution function. So let's do this in steps. So step 1 is, what is the probability of success in the first X trials? And then failure in the remaining n minus x. Okay, so what is the probability of success in the first X trials and then failure in the remaining n minus x? So let S sub I, let little s sub I equal the event of success in the ith Bernoulli trial. And let f sub I equal the event of failure in the ith Bernoulli trial. Okay, where I is going from 1 to n. Okay, and so this is for I equals, well, you have a first Bernoulli trial, a second, up to including the little nth. So these are both for those values of I. Okay, for both of them. Let me just get rid of parentheses. Okay. Okay, so you have those events. So now let's express the probability that we're asking to find. So what's the probability of success in the first X trials? So we want success in the first trial, success in the second trial, up to and including success in the Xth trial. Then afterwards, we want to look at failing every other time. So failure in the X plus first trial, failure in the X plus second trial, and so forth, up to including failure in the last trial, which is the nth trial. Okay. Okay. So that's the probability we want to find. Probability of success in the first X trials and failure in the remaining n minus x. That would mean you succeed in the first and succeed in the second and ... and succeed in the X and fail in the X plus first and fail in the X plus second and ... and fail in the nth. Okay, but these are all independent events, right? Whether you succeed or fail in one Bernoulli trial has no effect on whether you succeed or fail in another. And so they're independent. And so none of them have any effect on the other. So this is equal to the probability of success in the first times the probability of success in the second times ... times probability of success in the X trial times probability of failure in the X plus first trial times probability of failure in the X plus second trial times dot 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 times the probability of failure in the nth trial. Okay. Okay, so you have those probabilities and you multiply them. Okay, now we said that the probability of success is P and the probability of failure is Q. So this is P, so this is P times P times dot 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 times P, where there are X many of them, X, little x, many P's. And then this is times Q times Q times dot 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 times Q, where there are in n minus x many Q's. Okay, and so then that's equal to P to the x times Q to the n minus x. Okay, so the probability of success in the first X trials and failure in the remaining, or just success in the first X, success in the first X trials and then failure in the remaining n minus x would be P to the x times Q to the n minus x. But keep in mind, we have a very specific order. In the first, we want the probability of success in the first X trials, then failure in the remaining n minus x. So I'm going to bolden the words first, and then first X trials, and then remaining n minus x. So you see how the probability we found has a specific order of the successes and failures, right? We want success in the first X trials, and then failure in the remaining n minus x. And so this is only a probability with that order. If we wanted to find in general the probability of X successes, then we would have to take into account all the orderings of exactly X successes. And so this is only one ordering of exactly X successes in n Bernoulli trials. Okay, step 2 is going to be count the number of ways that you can succeed in exactly, that you can succeed little x many times in n Bernoulli trials. Right? Not the probability of succeeding x many times in Bernoulli trials, just the number of ways that you can succeed x many times in n Bernoulli trials. Okay? And so that number, okay, so the number of ways you can succeed exactly x many times in little n Bernoulli trials is just equal to the number of ways that, if you have a set with n things in it, to choose k of them. I mean, to choose x of them. So if you had a set with n distinct elements in it, the number of ways to choose x of them, that's the same as the number of ways if you have n Bernoulli trials, trial 1, trial 2, up to including trial n, the number of ways that you could choose little x many of those trials. That's ncx, right? And so this notation is representing the number of ways to choose x things in a set with n distinct elements in it. And that does not take into account order, right? It's just the number of ways to choose that many, right? Right. So for instance, if you had 3 trials and you want the first and third to be a success, you don't need first, then third, then third, then first, right? You just need the first and third to be successes and the second to be a failure. There's no order involved in which of the ones are success, right? The numbers are representing the different trials, not the order in which those, well, there is the order, but I mean, first, second, but it doesn't matter. You could actually do trial 3 first and then trial 1, or trial 1 then trial 3. The numbers are just denoting the fact that they're different trials. They don't have to be done in a particular order. Okay, so so the number of ways you can succeed x many times in Bernoulli trials, NCX. Okay, so step 3 is now calculate the desired probability. And that probability is the probability that in n Bernoulli trials, you have exactly x many successes, where the possible values of little x are 0, 1, 2, and so forth, up to including little n, the number of Bernoulli trials. Okay, so let's do that. So the probability that in n Bernoulli trials, that the probability that you'll have exactly x many successes is, well, it's n choose x. It's the number of ways to choose x of the n trials to be successes times the probability of when you choose those x, that x will be successes and n minus x, the remaining ones, will be failure. So P of S sub n equals x is equal to n choose x times P dx times Q the n minus x. And this is for x equaling to 0, 1, 2, and so forth, up to including n. Okay, and so that answers the question. Okay, this probability function is called the binomial probability function. Okay, so now we have the binomial probability function. So this is definition 4.5. Let little n be a positive integer. I'm just going to reiterate this now. Let little n be a positive integer, and let P and Q be probabilities with P plus Q equaling to 1. The function B of x colon n comma P is equal to n choose x times P the x times Q the n minus x for x equals 0, 1, 0, 1, 2, and so forth, up to including little n, is the binomial probability function. Okay, so this is the definition of the binomial probability function. D, there's exactly one. Okay, I mean, applied to different situations, but this is the form. Okay, definition 4.5. Let little n be a positive integer, and let P and Q be probabilities with P plus Q equaling to 1. The function B of x colon n comma P is equal to n choose x, P the x, Q the n minus x for x between 0 and 1 inclusive, is the binomial probability function. Okay, the one we just talked about is the binomial probability function. Little x, this first value, denotes, the little x here denotes the number of successes. The little n denotes the number of Bernoulli trials, and little p denotes the probability of success in a Bernoulli trial. Okay, so this little x value, there's a colon here, right? The colon is separating x and n comma and p, right? On the right is n and p. So you have an experiment that has n Bernoulli trials, and the probability of success is p in any of those trials. So the n and p are kind of expressing the experiment. To the left is the x. The x is saying, okay, well, how many successes do I want to think about? Do I want to think about 0, 1, 2, up to including n, right? So this little x is most likely to change. The n and, for an experiment, the n and p will stay fixed, right? For a given experiment, you'll have a set number of Bernoulli trials and you'll have a set number of probabilities. But then for that fixed experiment, you could consider any number of successes you want, right? As long as there could be that many successes. And so to the left is kind of the thing that in that experiment, you might change the value. Okay, so that's why there's a colon here. Okay. Okay. And so that's the definition of a binomial probability function. And then I'm going to say something very similar to the other things, the other distributions. A random variable has a binomial distribution and is referred to as a binomial random variable if its probability function is the binomial probability function. Okay, a random variable has a binomial distribution and is referred to as a binomial random variable if its probability function is the binomial probability function. Okay, so since here, if you have an experiment with this probability function, the binomial probability function, then you know your random variable is a binomial random variable and with a binomial distribution. Okay. Note. Note that b of x colon n comma p is equal to b of n minus x colon n comma 1 minus p. Okay, so this might look weird, but it's saying this. It's saying that if you have n Bernoulli trials and you have the probability of success is p, right? Then in a Bernoulli trial, what is the probability that in those n Bernoulli trials you have exactly x successes, where the chance of a success is p, right? Well, that's equal to this situation. It's equal to the situation where if you have n Bernoulli trials and you have the probability of success is 1 minus p, and you have n minus x many successes. What that's really saying is that the probability of x successes is the probability of n minus x failures, okay? Except here, instead of saying q is instead of saying, okay, what are the chances of failure? It's q, which is 1 minus p. I'm defining success as failure. I'm saying the chance of success, which was called failure, is 1 minus p, 1 minus the probability of success. And I want to succeed n minus x many times, okay? If you flip the word success and failure, it's saying the probability of succeeding x times is the same as the probability of failing n minus x times, right? Where the probability of success is p and the probability of failure is 1 minus p, right? But mathematically, right, you see this because if you have b of n minus x colon n comma 1 minus p, I start with this because it's the weirder one. This is equal to using the definition, right? This definition. Okay, I'm using this definition here. Then you have a total of n Bernoulli trials. You can see that here. And then you put this number down here. So this is n choose n minus x. I want to choose n minus x of the n trials. And then I'm going to succeed, but this is the p here is what I'm using here. So this is 1 minus p, the thing here, raised to this power, raised to the n minus x power. And then you have q, right? Q raised to the n minus this. Q raised to the n minus this, but this is n minus x, so it's n minus x. Okay? So you have n choose n minus x times 1 minus p raised to the n minus x times q raised to the n minus x. Instead of n minus x, it's n minus x. Okay. Remember q, so remember q is is 1 minus this probability. Q is 1 minus this probability. So I don't think the graph is the best way to see this. This I think drawing a graph would make things more confusing. If you have n choose n minus x, and you have 1 minus p, if you raise it to the n minus x, right? Q is 1 minus this thing. And so Q I'm going to replace with 1 minus p. And I'm going to raise it to the n minus, I'm going to do this one step at a time. So n minus x. So I'm just substituting Q for 1 minus this. Well, then that's equal to n choose x. I mean, n choose n minus x times 1 minus p raised to the n minus x. Then 1 minus, in parentheses, 1 minus p, you distribute the negative sign, so it's 1 minus 1 plus p. So you get p raised to the, you get p raised to the n minus x. It's n minus n plus x. You get p to the x there. And so now you have this. And now this is equal to, I'm just going to rearrange the terms. And so you still have n choose n minus x. And then you have, I'm going to put p to the x next. And then I'm going to put 1 minus p raised to the n minus x. Okay, but this, well this is, okay, so n choose n minus x is the same as n choose n minus x. And then the rest of it I'm going to keep the same. Okay, and so why is n choose n minus x the same as n choose n minus x? Because I remind you that I mentioned that if you have let's say n choose k, this is equal to n choose n minus k. Okay, so if you have n choose k, it's equal to n choose n minus k. An example of that would be if you had 5c2, 5c2 would equal to 5c3. Okay, another example would be if you had 7c1, that would equal to 7c, and then it would be 7 minus 1, and you'd be 7c6. See that? 5c2 equals 5c3, 7c1 equals 7c6. So here, 7ncn minus x is ncn minus x. And ncn minus x, I mean, ncn minus n minus x is the same as ncx. And the rest of it is the same. Okay, but n choose x times px times 1 minus p to the n minus x 1 minus p is q. And so this is the same. This is equal to, I'm putting every step in. So some of these steps can be, and this is q to the n minus x. And so that's equal to, q is 1 minus p. And so then that's equal to b of x colon n comma p. It's equal to b of x colon n comma p. Okay, and so I just showed us that this, which is this thing, is equal to this, which is this thing. Okay, so I just proved the note and I reminded you that relationship between different combinations. Okay, any questions? Okay. Example 4.7. So for part A, find the probability of getting exactly 4 heads in 10 flips of a coin. Okay, so this is a probability of exactly 4 heads in 10 flips of a coin. Well, that's equal to the probability of S sub 10 equaling to 4, meaning it's the probability that in 10 Bernoulli trials you have exactly 4 successes, where success is defined as getting heads. Okay, so here we are going to perform 10 Bernoulli trials, and we are going to define success as getting, as flipping. We're going to perform 10 Bernoulli trials. Each Bernoulli trial is 1 flip of the coin, of a coin. We are going to define success as flipping a heads. Okay, so if we flip a coin 10 times, that's 10 Bernoulli trials, and we're going to define success as flipping a heads. And so when you get heads, it's success, and when you get tails, it's failure. We could have defined it the other way around. We could have defined tails as success and heads as failure. But we made the choice to say that heads is success and tails is failure. And it's a good choice. The other choice would not be as good for this example, right? If we wanted exactly 4 tails in 10 flips of coin, then we would want tails to be success, right? Okay. So P of S sub 10 equals 4 is the probability of 4 successes in 10 Bernoulli trials. And so we can get this, once we write this notation, we don't longer even have to think about the experiment or what a success is or heads, right? We want the probability of exactly 4 heads in 10 flips of a coin. But we've expressed that probability in more general terms. We've expressed it as the probability of exactly 4 successes in 10 Bernoulli trials. Okay, and so nowhere in that notation do you even need the fact that you're flipping a coin. Okay, or what a success is. It's just 10 Bernoulli trials with exactly 4 successes. Okay, and so we've now expressed a very specific situation using very general terms. Okay, so now let's find that probability. And so the probability of exactly 4 successes in 10 Bernoulli trials is 10C4, the number of ways to choose 4 of the trials to be successes out of 10, times 1/2, which is the probability of success raised to the 4th power, times 1/2, which is the probability of failure raised to the 6th power. Okay. So I guess technically here we've said the probability of success is 1/2. Okay, so, and then we are going to define the probability of success as 1/2. So P is equal to 1/2. Okay, so we've also defined the probability of success as being 1/2, P equals 1/2. Okay, and so that's the probability of exactly 4 heads in 10 coin flips. And that's 0.2051. Okay, we've modeled the situation. We made the probability of success 1/2. Because the probability of flipping heads is about 1/2. Okay. Find the probability of obtaining exactly 12 sixes in 20 throws of a die. Okay, find the probability of obtaining exactly 12 sixes in 20 throws of a die, right? So if I asked you this question yesterday, or even just 2 hours ago, you might have been stumped for hours trying to figure out the probability of obtaining exactly 12 sixes in 20 throws of a die, right? That would be maybe a very difficult question. Now, if you get what I just taught you here, then it's very easy. What is the probability of exactly 12 sixes in 20 throws of a die? Well, you have 20 Bernoulli trials. Each time you throw a die, success is throwing a 6, and failure is throwing 1 through 5. So when you're thinking of Bernoulli trials, you're thinking of 2 possibilities, success or failure, right? Where you define what success is and what failure is correspondingly. That does not mean that there are 2 simple outcomes in the experiment, right? Your experiment could have many outcomes, right? And success does not mean one specific simple outcome. In this case, well, it doesn't, and failure doesn't have to be exactly one simple outcome. In this case, success is one of the simple outcome, but failure is 5 different simple outcomes of the experiment, okay? So here we are defining a Bernoulli trial as a throw of a standard 6-sided die. We are defining, we are performing 20 Bernoulli trials. We are defining success as throwing a 6 in any one roll of die. And we're just going to mention correspondingly, we are defining failure as not throwing a 6 or throwing a 1, 2, 3, 4, or 5. Okay, we are defining the probability of success as P equaling to 1/6, because there are 6 dice rolls, each equally likely to occur, and we're saying success is rolling a 6. So that's 1 out of 6, right? Probability of rolling a 6. And so we've now, with all these definitions, we've now taken, again, I'm going to say this thing again, we're taking an experiment, a very specific experiment, and we're expressing it in general mathematical notation. And so now that we've assigned all these values to things, we no longer even have to talk about the experiment itself. We no longer have to talk about rolling a die. We don't have to talk about rolling a 6, right? We don't have to talk about what's happening in any Bernoulli trial. We just have 20 Bernoulli trials. We have the probability of success being 1/6, and we want to find the probability of 12 successes out of 20 Bernoulli trials where the probability of success is 1/6. So the probability of exactly 12 sixes in 20 throws of a die is equal to, using our mathematical notation, it's equal to B of 12 colon 20 comma 1/6. Okay. It's the probability that in 20 Bernoulli trials, we have exactly 12 successes where the probability of success is 1/6. B of 12 colon 20 comma 1/6. This notation is expressing the probability of getting exactly 12 sixes in 20 throws of a die. And this notation isn't talking about dice rolls. It's not talking about sixes. It's not, right? It's just talking about Bernoulli trials, number of Bernoulli trials, number of successes, probability of the success. Okay, so it's really cool how you can express many different situations using the same notation. And this notation means you can remove any mention of even the experiment itself. Okay, so probability of exactly 12 sixes and 20 throws of a die is equal to B of 12 colon 20 comma 1/6. And you calculate that, and so that's the same as 20 choose 12 times 1/6 raised to the 12th times 5/6 raised to the, and then this is to the 8th power because it's 20 minus 12. Okay. Now, many of you will ignore my advice and go from here to here. I mean, you're getting it and you'll get the right answer. I mean, some of you, your understanding will stop and you won't go to this point. I encourage you to keep going. Some of you might end with this. Probability of exactly 12 6 20 throws of a die. You might skip this notation and go directly here. Right? I don't want you to do that. I want you to think of this notation. So you have 20 throws of a die, right? So you think, okay, I don't want to write this B thing down. I have 20 experiments. I want 12 of them to be successes. So 20 C12. And then here's the probability of success 1/6. You raise to the 12th power because there's 12 successes. Okay, and then failure is 5 6, and then the remaining 8 are failure, right? So you multiply them, you get this, right? And so maybe you'll say, okay, I can't remember even the order of these numbers, right? Where's the colon go, right? And you're like, I don't want to remember this. I'm just going to write this down. This makes sense, and it's right. You calculate it. You'll calculate it, and you get 0.1234135. Okay, so it's 0.0000135. Okay, that's the probability. Okay, it's because you calculated this, right? The number being 7 decimal points doesn't even, you're just plugging in the calculator, right? That's not hard. Okay, but I want you to see the power of this notation. I really emphasize, right? People get scared of mathematical notation and they see it and they say, this is weird. Why do mathematicians do this? Why do they write these strange symbols down that don't make any sense and think that this is a good idea, right? Why don't you just write down the thing that looks like the thing you're talking about? But this is really good because in 3 numbers, we've encapsulated the entire situation, right? When you're trying to answer a math problem and you boil the problem down to just writing down a symbol or a notation, and then the notation tells you what to do to get the answer, and that's really good, right? Because keep in mind, if you're doing this, you have to mentally think about the choices of each thing, and you have to think about, okay, probability of success is 1/6, you succeed 12 times, right? You're thinking about every step along the way with this product. Here, you're just writing down a few numbers, and then you're calculating it, and you're getting the whole answer, right? You have how many? You asked 3 questions, right? Ask 3 questions. Question 1: how many Bernoulli trials are there? There's 20 of them, right? You put the 20 there because you're throwing the die 20 times, right? 2: how many successes do you want? Right? you want exactly 12 sixes in 20 throws of dice. So you want exactly 12 sixes. So you want 12 successes. And then third question, what is the probability of success? Well, if success is throwing a 6, then probability of success is 1/6, right? You plug these numbers in. You answer these three very simple questions. You plug the numbers into here, and then you write this notation down without even knowing what the answer is, right? And then if you can calculate this, you now get this expression and you get the answer. So the notation is telling you how to do the problem, right? So what you need to know is, okay, so you need to know, so let's say I called step 1, right? Write down this, right? B of x colon n comma p is equal to n choose x times p to the x times q to the, and I'm going to actually put this way, I'm going to put 1 minus p raised to the n minus x, okay? You just write that down, all right? Step 1, write that down. Step 2, ask 3 questions. 1, how many Bernoulli trials are there? That's the value of n, little n. How many successes do you want? That's the value of little x. What is the probability of success? That is the probability of little p. Okay? And then step 3, plug those values into the formula in step 1. Okay, all of these 3 steps are easy to do. Okay, you just write down this formula. Step 2, you ask these 3 questions. The answers are the values of n, x, and p correspondingly. Step 3, plug in those values there. And then you're done. And that's the problem, right? And maybe you have to remember some things, a few things, but there's no actual there's not much thought. There's not much creative thought needed to do this problem. I can give you something that looks pretty like this, even this problem, B. Find the probability of obtaining exactly 12 sixes and 20 throws of a die, right? You could spend 6 hours trying to solve this problem and still not get the answer. But now, just asking a few very simple questions, doing these 3 very simple steps, boom, there's the answer, 0.0000135. Okay? Power of mathematical notation. So that's part B. Okay, so let's look at an example. Example 4.8. If the probability of recovery from a certain disease is 0.20 and 10 people came down with the disease, what is the probability that at most 3 of them will recover? Okay, so just like many kind of math situations, I've now taught you, how to find that probability in the previous example. Now I'm going to build on that, and so now we're going to add one additional difficulty to a problem. Okay, so if the example 4.8, if the probability of recovery from a certain disease is 0.20 and 10 people came down with the disease, what is the probability that at most 3 of them will recover? So now the question isn't asking you find the probability of exactly a certain number of successes. It's asking you to find the probability of at most a certain number of successes, at most 3 successes. Okay, so that's just a little additional thing. It's not too difficult. Okay, so let's define what a Bernoulli trial is, a success in a Bernoulli trial, and the probability of a success in a Bernoulli trial. Okay, we're not counting each, we're just defining each. Okay, so I'm going to put this example on the next page. Okay, so let's call a Bernoulli trial. So let me ask you that. So I'm going to ask the following questions. What is a Bernoulli trial in this example? What is a success in a Bernoulli trial? And what is the probability of success in a Bernoulli trial? Okay, so I'll give you maybe a minute to get this answer. I'm going to plug in my charger so my computer doesn't die out. And while I'm doing that, define yourself each of the three. Define a Bernoulli trial, success in Bernoulli trial, probably a success in a Bernoulli trial. Okay. Oh, don't say the answer yet. Okay, so can someone answer to me tell me what are Bernoulli trials in this example? Anyone? What is this? What is a Bernoulli trial in this example? Okay, so a Bernoulli trial is a person gets sick from a certain disease. That was probably the hardest of the three. Okay, a person gets sick from a certain disease. That's a Bernoulli trial. What is the success? A success is that a person recovers from that certain disease. Okay, that's a success. A person recovers. Now, actually, you'll see that success doesn't necessarily have to be good, right? If we were talking about, we could have gone the other way and said that success is someone not recovering, right? So success doesn't have to mean something good happens, or success doesn't even have to mean something you really want. Okay, in more general terms, we just have success and failure as two polar opposite outcomes. Okay, so success is what you define it to be, right? Success is what you define success to be, right? Okay, so it depends on what you're asked in the problem to find, right? Success is usually going to be corresponding with what you want to find in the problem, not what you want to happen. You want people to feel better, I hope. So you want success to mean that somebody recovers, but if the problem were to say, was the probability that most three of them will not recover, then you'd probably want success to be that they don't recover. Okay? Yeah, and so the probability of success, right? The probability of success, which is known by little p, the probability of success, I'll just write the number, is, so wait, no, wait, sorry, no. Sorry, I want to agree with you, but it's not 3 out of 10. The probability of recovery from a certain disease is 0.20. the probability of recovery is 0.20. I'm just going to put space here to separate from the rest of this. You can see it better, right? We want the probability, in the end, we want the probability that at most 3 of them will recover. But we want at most 3 to recover out of 10, right? We're doing 10 Bernoulli trials, and we want the probability of at most 3 successes in the 10 Bernoulli trials, right? If there's 10 people that get sick, we want to know what is the chance that at most 3 of them recover. Well, each individual person gets the disease, either recovers or doesn't. And so for each of the 10, the Bernoulli trial is that any one person, any one of those 10 gets sick. That's the Bernoulli trial, right? Success is that that particular person recovers. The probability of success in a Bernoulli trial is the probability that that person recovers from the disease, which is 0.20, okay? So probability of success in a Bernoulli trial is 0.20, right? Probability of success in a Bernoulli trial is not the same as the probability we want to find. We want to find the probability of it that at most 3 of them will recover, that we have at most 3 successes in 10 Bernoulli trials. But each Bernoulli trial has its own probability of success and failure, right? It's like if I flipped the coin 10 times and said, what is the probability I get at most 10 heads? I mean, at most 3 heads, right? What is the probability I get at most 3 heads in 10 coin flips, right? That's not the same as the probability in any one coin flip of getting heads. That's 1/2, right? Flipping a coin and getting heads, that's a 1/2 chance, right? In any one coin. But the probability of getting at most 3 heads in 10 coin flips uses the probability of 1/2 to get that, right? So we're going to use the fact that each person has a 0.20 chance of recovering from the disease to find the probability that most 3 of them do recover. That makes sense? So the probability of success in this Bernoulli trial is 0.20. Does that make sense? Person who said 3/10 in the chat. Kishan, does that make sense? That was a good guess. That was a good try, right? 3 out of 10 is a good try. 3 out of 10 is probably what you normally think it is, but things have changed a little bit now. Bernoulli trials are a little different, right? So you have to visualize what a Bernoulli trial is and what the probability of success in a Bernoulli trial is, right? So you have to, it's a new thing. Okay, good. So we have, good. Okay, you got it. Good. So, okay, so we have these things, right? And so to really get this, you have to just do more examples, right? I think you get this example so far, right? When you see another example, you have to learn how to distinguish on your own what a Bernoulli trial is, what a success in a Bernoulli trial is, and what the probability of success is, right? Once you practice it a few times, once you practice it enough, and you start getting it right enough times, it can start to become easy, right? Right now, you're just learning it. It might be a little hard. Okay, so we define these things. Okay, so again, I don't have to write out all these words usually, but I'm doing it to help you learn it, right? So we want to find the probability that at most 3 of them will recover. Well, that's equal to the binomial probability, the value of the binomial distribution. Well, okay, so we're going to have a colon and we're going to have a comma. So I want to put the number of trials first because it's the easiest. Okay, 10 of them come down with disease. So we have the number 10 here after the colon. The probability of recovery, we said, was 0.20, right? And, oh, sorry. The probability goes to the right. 0.20, that's the probability of success, right? Probability of recovery is 0.20. There's 10 people who get sick. And we want to find the probability that at most 3 of them will recover. Well, that's equal to the probability that 0 of them recover plus the probability that 1 of them recovers plus the probability that 2 of them recovers plus the probability that 3 of them recovers. Okay, the probability that 0 of them recover plus 1 plus 2 plus 3, right? There's no overlap in these chances, right? You can't have 0 people recover and 1 people recover at the same time. Okay, so I'm going to write here, I'm going to write in words what that notation is saying. This is the probability that 1 recovers, exactly 1 recovers, plus the probability that 2 recover, plus the probability that 3 recover, plus the probability that 4 recover. Okay, so probably, oh, there's only 3. Okay. Okay. This should be probability that 0 recover. Plus the probability that 1 recovers, plus the probability 2 recovers, plus the probability 3 recover, right? Okay, and so this is equal to, this is saying this value, this is saying this one, this is saying this one, and this is saying that one, right? So now we've broken down the problem to finding each of these 4 probabilities, where each of them could be expressed using the notation I just described, right? You have a certain number of Bernoulli trials, you have probability of success in each Bernoulli trial, and you want to find a certain number of successes in those 10 Bernoulli trials. 0, 1, 2, or 3. At most, 3 of them recover. Does that make sense? So, okay, so now it's just a matter now you calculate each of them, and then you and then you add up the values. Okay, so I'm going to do this, and then I'm going to copy this. Okay, so you have 10 Bernoulli trials, and then this. Actually, so what I'm going to do also is I'm going to remind you of this notation right here as I copy this down. Reminder, that, right? That's how you calculate that. And so this is how you don't even have to think about what you just follow this notation. 10C0 times P, which is this number, raised to the 10th, raised to the 0th power, and then times 1 minus that value raised to the 10 minus 0, which is 10th power, plus, okay, okay, then you have 10 choose 1 times probability of success 0.20 raised to the 1st power, and then times 1 minus 0.20 raised to the 9th power, then plus 10C2 times 0.20 raised to the 2nd power times 1 minus 0.20 raised to the 8th power, plus, I guess it's good to visualize the notation and to be able to see it while writing it down. Okay, so then 10C3, this would be annoying to refer to the notation every time writing this down, times 0.20 raised to the 3rd power times 1 minus 0.20 raised to the 7th power. Okay. Okay, and so when you calculate this, get this is equal to 0.1074 plus 0.2684 plus 0.3020 plus 0.2013. This is equal to 0.8791. Okay. That's the probability that most 3 of them will recover. Good. Okay, and so that's that. Okay, so we're going to stop there for today. Okay, so we finished the binomial distribution, sampling with or without replacement. We didn't have time for today, so we're going to do that next class. So a few reminders. Okay, so sections in 4. This was the homework I assigned last class, and I said except 4.4. 4.4. 4.4, I just illustrated with the bar chart and the other thing, right? So now 4.4 is now going to be including 4.4, right? And so I'm adding this one section now, and it's due tomorrow, Tuesday, July 27th at the start of class, okay? So I'm including, so it's the entire homework 4, right? And so homework 4, here we go, homework 4. This is homework 4. So this is what's due tomorrow, right? Okay, so hopefully you worked on it over the weekend. And so I'm just adding this one more question. Draw a histogram and bar chart of the random variable x in example 4.3. Oops. Okay. So, okay. So, example 4.3. It's this guy. Okay. This is our example 4.3. Okay. So I'm going to go to today's lesson. Okay. In homework in 4.4, we have this example referred to. So in homework 4.4, okay, it's referring to this example 4.3. Okay, so it's from the notes. It's not talking about the homework problem. Okay, so 4.4. Okay, it says in example. Whenever it says example 4. Example something, it means example in class. Okay, so example 4.3. The notes are all online, so you can find this right online, right? So example and the number, everything is in order. So even though that it's weird, it's going in order. Example 4.7 is after example 4.3, right? So you would go back in time to 4.3. All the notes are online on Blackboard, and you can find example 4.3. But I put it down here for you, okay? So this is the example it's referring to, and it wants a histogram bar chart of that random variable. Okay. Okay. 3 flips of a coin, number of heads in the 3 flips. Possible values are 0, 1, 2, and 3. What are the probabilities of each of them, right? And then express it using a, sorry, let me go back one time, using a histogram and a bar chart. So those two, one each, okay? Okay, but again, reminder, test 1 is on July 29th during class, and it's going to start very soon once class starts. It's from 10 a.m. to 11:34 a.m. Use the same normal class length to attend at, and homework 4, including 4.4, is due tomorrow at the start of class. Okay, and so that's that. So Kishan, you don't have to remind me. I'm now going to save the whiteboard, and so we're done for today. Okay, so I'll see all of you tomorrow. Thank you for being here. and have a good day.
Okay, thank you.
You're welcome. Okay, bye, everybody. Have a good day.